Alright, welcome back. This is section 4 on the topic simple harmonic motion. Please do well to watch section 1, 2 and 3 before watching this one. Let's continue. A simple pendulum clock or a pendulum clock is built on Earth and taken to the moon. The acceleration due to gravity on the moon is 1.63 meters per second squared. The clock runs faster compared to the Earth, true or false? So the answer is false. The clock actually runs slower. How do we prove that? Again, remember that period is equal to 2 pi L over G. This implies that period and acceleration due to gravity are inversely proportional to each other. So I can say period is inversely proportional to the square root of G. Okay, that means if G decreases, period will increase, and increase in period actually means decrease in speed. Let's prove that. We saw another formula connecting period and speed. That's T is equal to 2 pi R all over V. Do you remember from the popular formula T is equal to 2 pi over omega? Alright, so if you plug in the value of, remember V is equal to omega R, so omega itself is equal to V over R. So if you plug omega into this, you are gonna get T is equal to excuse me, T is equal to 2 pi R all over V. So this means that if period increases, the speed would decrease. So the answer is false. Alright, a simple pendulum makes 90 oscillations in 1 minute on the Earth's surface. The number of oscillations a minute which the same pendulum will execute at an altitude where the acceleration due to gravity is 81% of its value on Earth is dash. Okay, now I need to concern myself with frequency and G. So I'm comparing frequency to G, or I can even decide to compare omega to G, or comparing the two of them, omega and G. Of course, I know that omega is equal to theta, angular displacement all over time, and theta is 2 pi times the number of cycles or oscillations, if it must be in rad, all over time, which must be in second. So anyone I like I use, but let me use omega, after which I will use frequency and G. Now I know that omega is equal to the square root of G all over L. Don't be confused. Okay, remember that T is equal to 2 pi over omega, but as T is also equal to 2 pi square root of L over G. So if you work this out, let me claim here, if you work this out, you will notice that omega is equal to square root of, just turn this, G all over L. So what's the implication of this? It means that omega is directly proportional to the square root of G. Remember, in relationship problems, you concern yourself with just the parameters that are captured in the question. Every other parameter not captured should be rendered 0. I've often said that. So with this, I can establish my ratio omega 1 all over G1 is equal to omega 2 all over G2. Now omega 1 Omega 1 is 90, okay, oscillations per minute for 1 minute. Okay, now G, I can say G1 equals X. Use any variable of your choice. G2 will now be what? 81% of X. Alright, so if we plug in the values, we will have that 90 oscillations per minute all over square root of X, since I'm calling G1 X, is equal to omega 2, which is what I'm looking for, all over square root of 81x all over 100. Now, if I cross multiply, I will have that omega 2, okay, it will be equal to 90 times square root of 81x over 100 divided by square root of x. Okay, so this again implies that omega 2 is equal to 90 times square root of 81x over 100 divided by square root of x. So let me finish it up here. Omega 2 is equal to 90 times square root of 81 over 100 times square root of x. I'm actually separating x from 81. Okay, then times 1 all over square root of x. In order to remove the sign of division, the division sign, and replace it with multiplication sign, remember you invert whatever you have there, and that's what is happening. Now this takes care of this, and then we have omega 2 is equal to 90 times square root of 81 over 100. Okay, so this is 90 times 9 over 10, and 0 cancels 0, and then our answer is 81, and that's the answer. Now if you also wanted to use frequency, you could have done this. Remember that frequency is equal to 1 over 2 pi square root of g all over L. Alright, from this you can as well see that f is proportional to the square root of g, and we could have done the same thing we did before. Alright, the next question. A simple pendulum of length 0.4 meters has a period of 2 seconds. What is the period of a similar pendulum of length 0.8 meters at the same place? Okay, now this also has to do with relationship problem. Remember, we are comparing what here? Length and period. So I know that period is equal to 2 pi square root of L over G. So since I'm comparing period with length, every other parameter should be rendered 0. Remember, this is a constant. G should be called 1. Sorry, not 0. It should be rendered 1. Should be called 1. Alright, so T is proportional to square root of the length. So if I remove the sign of proportionality, of course I will have T is equal to K square root of L. Alright, this implies that T1 all over square root of L1 is equal to T2 all over square root of L2. Okay, so just plug in the values. For the first one, the first part of the question, T1 is 2 over L1 0.4 is equal to T2 is what we are looking for. So T2 all over square root of 0.8. Now, if we make T2 the subject, then we will have that T2 is equal to 2 times square root of 0.8 divided by square root of 0.4, and this is the same as 2 times square root of 0.8 all over 0.4. Okay, 2 times, now this divide this will give us square root of 2, so the answer is 2 root 2, and that's the answer. Alright, so a bulb of weight 0.1 Newton hangs from a massless string of length 50 cm. A variable horizontal force which increases from 0 is applied to pull the bulb. The string makes an angle of 60 degrees with the vertical. The work done is dash. Alright. Now remember, if we have our simple pendulum, this point, if this is raised to a certain height like this, okay, we don't use this other part, but let me still establish it. Okay, just use only one part. This side and this side are just a kind of mirror image of each other, so we normally concern ourselves with the mean, the extreme positions. So let's consider here A and B. Now if this is raised from here to here, can you see the height becomes well pronounced? So between here and here, this is the height, which is H. Alright, meanwhile here will be, remember the length is 50 cm, which is equal to 0.5 meters. Okay, and the angle is 60 degrees. Hope this is visible enough. 60 degrees. Now this point is L cos of the angle, while here is L sine theta. Hope you've not forgotten. We had earlier on seen the formula for height as regards simple pendulum. Okay, so potential energy will be equal to the work done in raising this pendulum bulb from this point, from the mean position to this height, from the mean position A to height B. Okay, so work done will now be equal to mgh, but h will be equal to L minus L cos theta. Remember that the total length here, this total length is still the same thing here, from here down to this place. Alright, so to find h, we just say the total length minus L cos theta to get h. Alright, so if we plug this in, we'll be having that work done will be equal to mg, okay, L 1 minus cos theta. Alright, so let's plug in the values. They gave us weight, and we know that weight is equal to mg. So weight is 0.1 times the length is 0.5. Now 1 minus cos 60 degrees. If you punch this, you are going to get 0.025 joule, and that's the answer. The acceleration of a body performing simple harmonic motion is constant and always directed towards the equilibrium position. True or false? Is false. Now it's not constant. Remember, for a body undergoing circular motion, not simple harmonic motion, circular motion, the acceleration is the magnitude of the acceleration is constant, but the direction is always changing. But when it comes to simple harmonic motion, the magnitude always changes. So this point, remember that acceleration at this point is 0. Okay, then it begins to increase, and at this point you have acceleration is maximum. Hope you've not forgotten. Acceleration at the extreme position is maximum. Meanwhile, at the mean position or the equilibrium position or the central position, acceleration is 0, and v here is maximum, and of course v here okay, is 0. All right, so the acceleration increases from 0. It keeps increasing the magnitude until it becomes maximum. So the acceleration is not constant for S.H.M. But for circular motion, of course, the magnitude is constant, but the direction is always changing. So the answer is false. Thanks for watching.